Recorded. So this is lecture number 23, and today we'll be talking about some particular topics on strain. One is dilatation, the other one is plane strain, and the third one is differential displacement, and how to resolve that into its components. Okay, so before we start, let's quickly recap as to what we did last time. So we talked about the infinitesimal deformation theory. So we said that the strains, the finite strain tensors that we had constructed, the Lagrangian and the Eulerian strain tensors, capital E and small e, they had a problem that they had non-linearities because of the product of use, as we see in the first term here. So what we did was we said that if we can somehow get rid of this term, then our theory of mechanics with strains in it becomes particularly tractable mathematically, as we'll see in the future. So what we did was we assumed that the situation where these things can be ignored is when the displacement gradient values are very small. So ui comma a, that's a displacement gradient. If these quantities are small, then the product of these quantities are much smaller than the quantities by themselves. So if we assume infinitesimal deformation theory, infinitesimal deformation, we get the infinitesimal deformation theory, and in that case, we saw that finally we have something called epsilon, which is so both Lagrangian and Eulerian strain tensors. They both boil down to just one quantity, which we call epsilon, or the infinitesimal strain tensor. And we'll be dealing with this strain tensor from now onwards. So from now onwards, we will assume that the infinitesimal deformation theory is valid. So this epsilon is defined as half of ui comma j plus uj comma I. So ui comma j is del ui by del xj small x, and uj comma I is del uj by del small xi. So we can clearly see here that it is symmetric by definition. It's ui comma j plus uj comma I. So that's the symmetric part of ui comma j tensor. So epsilon is symmetric by definition. Now then we started interpreting the components of epsilon, because we want to get some kind of a feel as to what the components of epsilon, what these values mean geometrically. So starting with the same measure as the square of the deformed length, d small x squared, minus the square of the initial undeformed length, d capital X squared, what we finally saw was that if we assume these initial undeformed vectors in the coordinate directions, in the Cartesian directions, that is I1, I2, and I3, uh, epsilon 1, 1, epsilon 2, 2, and epsilon 3, 3, that's the diagonal components of epsilon, they denote the longitudinal strain. So they basically denote the change in length in the coordinate directions. So the diagonal components of epsilon tell us how the body is stretching in the Cartesian or the coordinate directions. So that is E1, E2, and E3, which is the same as I1, I2, and I3 in this case, as we can see from the figure on the top. Okay. So this gave us a feeling of what the diagonal components of epsilon mean. And then we started exploring the interpretation of the off-diagonal terms of epsilon, that is the non-diagonal terms. So there we saw, after doing some algebra, we finally got something called a gamma. Sorry, and this gamma was given as n1 dot 2 epsilon dot n2. So what that basically means is that, I mean, if we take n1 and n2 in, let's say, in the Cartesian or the coordinate directions, so in this case we took n1 equal to I1 and n2 equal to I2. So we see that they are both perpendicular to each other. So that right angle, when the body gets deformed, changes to an angle which is something else. But remember that it's an infinitesimal deformation theory that's being valid. The right angle changes slightly. So gamma was that change in the right angle as the body gets deformed into the deformed configuration. Okay, so we could write gamma. So gamma ij was written as twice of epsilon ij for the non-diagonal terms. So if you start with two perpendicular vectors, then gamma basically tells you what's the change in the angle, the change in the right angle as the body gets deformed. And since the deformation is infinitesimal, so the change in angle gamma, which is non-zero, is also small. So gamma is a small value. That's the reason we could approximate sine gamma as gamma. So that's where we stopped after getting a good feel of the diagonal and the off-diagonal terms of the infinitesimal strain tensor epsilon. So that's where we stopped. Interpretation of the off-diagonal terms of epsilon. So we wrote gamma as equal to n1 dot twice epsilon dot n2, where n1 and n2 are perpendicular. So this was where we defined gamma, and later when we took n1 and n2 as the coordinate directions, two coordinate directions, then we got epsilon, epsilon ij instead of just epsilon here. But remember that n1 and n2 can be any two perpendicular directions that we desire. So we also know that the principal directions of a second order tensor are mutually perpendicular. So we can take so if n1 and n2 are principal directions of epsilon, it's still valid, so we can use the above relation. So what we get is gamma is equal to n1 dot 2 epsilon dot n2. Now what we know that the meaning of principal direction is that epsilon times this direction is the eigenvalue of the principal value times that direction. So what that means is this simplifies to twice epsilon 2, where epsilon 2 is the principal value or eigenvalue. So that's the second eigenvalue for the second eigendirection. Okay, so we have used the rule Ax equals to lambda x. So now epsilon is simply a scalar, it's an eigenvalue, so we can take this out. So we get twice epsilon 2 times n1 dot n2. And since n1 and n2 are both mutually perpendicular to start with, so this is 0. Right? So what we see is that if we take n1 and n2 in principal directions, our gamma is 0. So what was gamma? Gamma was the change in the right angle as the body gets deformed. So if gamma is 0, that means the right angle stays a right angle. Now the vectors may rotate as a whole, but the angle will still remain the same. So what we see for as a special case for any epsilon is that the principal directions stay mutually perpendicular as the body gets deformed. Now, what's interesting here is that if we take a small cuboid along the principal directions, Okay, it's a small cuboid. That means that the vectors are infinitesimal in length. So let's denote three directions as x1 star, x2 star, and x3 star. All right. So that's the our Lagrangian or the material coordinate system, but we have taken that in the principal coordinate system. So that's the reason we have a star here. So these are special directions which are called the Eigen Directions in this case, or the principal direction. So these are the principal directions of epsilon. So we take a small cuboid in this direction. So remember that everything is happening at around the point P. That's where we have defined the strain. So we define a small cuboid here. So it has one of so the this direction is dx3. This we call dx2, and this we call dx small. So that's our small cuboid. So when the body gets deformed, what we have seen is that this will still remain cuboid. So the angles may slightly rotate. My drawing is not that perfect, but I'm sure you can understand what I mean here. Well, it's the right angles still remain right angles, but of course the lengths may change. So the length in this case we'll call it d small x3, we'll call it d small x2, we call it d small x1, because remember that d capital X vector goes to d small x vector, okay, but they are mutually perpendicular. So now what we'll do is, since it's mutually perpendicular, so we can easily find the volume of this. So what we have to do is we have to see, so dilatation is the change in volume upon initial volume. So since the lengths are changing, so this new cube on the right hand side will have a different volume. So we want to see how the volume changes in the body uh, as the deformation happens. Okay, so we'll try to calculate. We will want to calculate dilatation, which is delta V by V. So initial volume is easy to find. It's simply d capital X1, d capital X2, and d capital X3. Just for clarity, what we'll do is we'll use superscripts. So V initial, okay, so that these are the lengths. Okay, so they're the same as d capital X subscript 1, but just for clarity, I've used superscripts. So that's the initial volume, and then the final volume is d small x1, d small x2, and d small x3. So you'll see that I have not used a vector sign here because we're talking about lengths in this case. Now what we'll want to do is we'll want to write d small x in terms of d capital X, and we can easily use that, write that using our longitudinal strain definition. So we defined longitudinal strain which we denote as E n hat. So the n hat basically tells us that it's which direction we're talking about. Okay, so longitudinal change in length in a particular n hat direction. So this is d small x minus d capital X divided by d capital X. So that was the definition of longitudinal strain, and we could write that as n dot epsilon dot n. So that's from what we derived last time. Okay. So we derived that this quantity longitudinal strain, which is d small x minus d capital X by d capital X, that's the change in length upon unit length, is equal to n epsilon n. So if we substitute the values that we have here, so we can easily write d small x1 minus d capital X1 divided by d capital X1 is epsilon 1. Okay, that's epsilon 1 1, but we know that we're talking about principal directions. So in the principal directions, our epsilon 1 1 is simply so epsilon is a diagonal tensor. So the first epsilon 1 is simply one of the eigenvalues. Okay, so epsilon 1 1 is the eigenvalue epsilon 1. So if we just move around the terms in this case, so what we get is d small x1 is equal to epsilon 1 . So then we can write delta v by v as so this is d small x1, similarly d small x2 is this, and then that's d small x3. So that's the volume in the deformed configuration, and I can subtract the volume in the undeformed configuration, that's this, divided by the volume in the undeformed configuration. Okay, now we simply have to open the brackets, and when we do that, let's write that. So we'll take d capital X1, d capital X2, and d capital X3 common. So they come from these terms. So d capital X1, d capital X2, and d capital X3, they can be taken common. And then we have a term which has 1, which is from the product of all ones. Then we have epsilon 1 plus epsilon 2 plus epsilon 3. And then we'll have terms which will have either a product of two epsilons, or we'll have one term which will have epsilon 1, epsilon 2, epsilon 3. So I'll just call it small terms, because remember that it's an infinitesimal deformation theory. So the epsilon values are also small, because epsilon values were nothing but ui comma j plus uj comma I. So since ui comma j, uj comma I, they're all small, so epsilon values are also small. So the square of small terms, or the product of two small terms and the product of three small terms, are too small as compared to epsilon 1, epsilon 2, and epsilon 3, and 1. So in fact, 1, you'll see that the 1 will cancel out. That's the reason we can retain epsilon 1, epsilon 2, epsilon 3 in the first approximation. So this 1 gets cancelled out when we subtract the initial volume. Okay, and then we are dividing by d capital X1, d capital X2, and d capital. Okay, so what we'll see is that this becomes, well, we should use an approximate sign here. So we neglected the small terms like epsilon, 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 epsilon. So what we get is finally that the change in volume per unit volume is the trace of the epsilon or the strain tensor, because we know that this sum is an invariant. So this is epsilon II, which is the first invariant of epsilon. Because you don't really need to be in the principal directions. You could be in any coordinate system. You could transform epsilon into any coordinate directions, and still the trace will be the same because it's an invariant. So sometimes people get confused that why are we taking in the cube that we started with in the principal directions, as I showed in the previous slide, why were the dimensions small? The reason is because to be able to apply this analysis, we can only talk about information which is close to point P, because epsilon is defined at point P. So if the cube was large, that is this, instead of having d capital X1, d capital X2, d capital X3, you had large dimensions, then you could not use the epsilon value around point P. You will have to integrate the information. Okay, so since we have the strain value at a point P in this continuum theory, then we can only talk about infinitesimal cubes around point P when discussing about dilatation. So what we have learned is a very important relation, that the trace of the epsilon tensor talks about the change in volume upon initial volume. In this case, as we have talked about, for a cube in the coordinate directions. Oh, sorry, in the principal directions. Okay, so later in the problem set, you will be asked to generalize the idea for any direction, not just principal directions. Okay, but for now, we're talking about principal directions only. So the strain tensor epsilon, as we did for the stress, can be split into two parts. So one's called the spherical part and the other is called the deviatoric part. So the spherical part is the isotropic part, as we discussed rigorously in the stress tensor. The isotropic part is given as the mean strain, which is nothing but the trace divided by 3 times delta Ij. It's an isotropic part, so we have delta Ij, and then we have the deviatoric part, which is everything except the isotropic part of epsilon. So again, I won't get into details of this discussion of spherical and deviatoric because we already have discussed these ideas in stress when discussing about the stress spherical and stress deviatoric parts. Okay, so they are exactly the same in terms of mathematics. The next topic is plane strain. So just again, as we talked about plane stress, the ideas are very similar. So we say that if a state of plane strain exists in the direction x1, x2, so we're saying that if a state of plane strain exists in x1, x2 plane at a point P, okay, so we're talking about the plane strain in x1, x2, because we have to define a plane. So we take the x1, x2 plane at a point P, because everything is being talked about. Epsilon is defined at a point P. Then the epsilon will look something like this. So that's how the epsilon looks when we have a situation of plane strain existing in a body in the x1, x2 plane. There's the same ideas as plane stress. So in the third plane x3, there is no strain. Now, this is only at point P. Now, if you want to say that the plane strain exists in the whole body everywhere, then you have to make sure that the strain looks like this in each and every x1, x2 plane. That's for every x3 direction. If you take slices at different x3 values, you have infinite slices. So at each slice, the epsilon should look like this. So that's what a plane strain looks like. Okay, so we won't go into details of the different situations where you have plane strains, but right now, all that's important is to understand what plane strain looks like. That's what this course is about. So this course does not give you a lot of. I mean, this is about the theory of quantum mechanics. So we will not talk about too many applications because any course that you take after this course, be it fluid mechanics or solid mechanics, that course will rigorously use these ideas and talk about with different physical situations or engineering situations. So this course is developing a theory, an elegant theory of quantum mechanics, which will give you all the tools available so that you can start applying this for different engineering designs. So now there's a very important idea. So let's think of a strain situation. So let's take a beam. So it's cantilever beam. So if you've not heard of cantilever beam, so what you do is you take some sort of rectangular extruded it's a steel element. You may have seen that during construction. It could be any cross section. Right now we've taken a box kind of cross section. It could be an eye cross section and so on. It's a cantilever beam. That means that it's fixed at one point. So it's just like a diving board in a swimming pool. So if you stand on this end, then the whole thing can go down or deform. So it's basically a diving pool and swimming pool is nothing but a cantilever beam. Okay, so the reason I'm talking about this thing is because as as you stand on the right hand side of this cantilever beam, what you see is that the beam deforms. So if we take the top surface, then what we'll see is that there'll be different deformations in different direction. So it's very difficult. So if I want to let's say a point P at the top surface, I would want to figure out when a person stands on this cantilever beam on the right hand side, how what is the strain value at point P for a given deformation. So as an engineer, you would want to quantify the value of strain. You will want to put 9 numbers there. But how do you measure that? So it's extremely difficult to measure shear strains because these are change in angles in certain planes, and it is not very straightforward to measure that. But measuring elongation is very straightforward. So what we do is we use something called a strain gauge. Okay, strain gauges are used to measure longitudinal strain, that is E n hat. So if you remember that E n hat was nothing but equal to d small x minus d capital X divided by d capital X in the n hat. So where d capital X was in the n hat direction to start with. So in the undeformed configuration, the d capital X was taken in the n hat direction. That's the longitudinal strain in the n hat direction. So strain gauges can measure that. So there are different, there are different products, different designs available for the strain gauges, which use different ideas for measuring strains. And one of the cheapest and the most common that we use is rosette. So what you do is, rosette is more of a configuration of strain gauges. So let's take one design. So what you have is it's a very thin transparent film with which is sticky at the bottom. So it's like a cellophane paper that you have. So it's a very thin cellophane paper which is transparent or translucent. And what you do is you have a conducting material that's going which is pasted on the top of this cellophane, and this is called a strain gauge. So what you can do is you can paste this on the body. This is a very this is exaggerated, so it can be very small. So you paste it, and then let's say you want to find the strain at point P. So what you can do is you can find the point P, you can paste it with point P in the middle of this strain gauge, and when the body elongates in this direction, then what happens is the length of these wires, or the total length of this wire that is going in a tortuous path, that total length increases, and as the total length increases, the resistance will change. So what you can do is you can connect it in, usually you use a Wheatstone bridge to balance the voltages and find the change in length. But you can use any electronics idea uh, to find out what the change in resistance of this is. And you already have a calibrated chart available to you, which tells you that which tells you corresponding elongation and the corresponding change in resistance of this strain gauge. It could be linear, it could be non-linear. We don't care about that as long as we have that calibration chart that tells us the mapping between the elongation and the change in resistance of the strain gauge. So once the resistance changes, you you measure that resistance, you convert that to elongation, and that gives you the elongation or in this direction, and that can then, well, actually it's a change in resistance, so it's the change in elongation that you see, and that gives you the strain in this direction. Okay, so you can measure the longitudinal strain, which is nothing but the change in length per unit length, using a strain gauge like this. So we have a particular situation where we take three strain gauges and connect them in a delta configuration. So let me show you this configuration. So we call it a delta rosette. Okay, so this is my x1 direction, that's my x2 direction, and then I can call this direction as x1 prime, and I can call this direction as x1 double prime. It's just a label. Okay? So x1 and x2 are the two directions in this situation, and x1 prime and x1 double prime are just labels being given to two directions. Now this is an equilateral rosette, equilateral delta. So this angle that you see here is 60 degrees. So then this angle becomes equal to, so we have a 90 degrees here, 30 degrees. Okay, so so this is called a delta rosette. Now remember that to find the strain at a given point P, now x1 and x2 are the two directions. So to find the epsilon in this case, and this is a plane strain situation, so our epsilon looks like epsilon 1 1, epsilon 1 2 0, epsilon 2 1, epsilon 2 2 0 0 0, something like this. So we want to find out epsilon 1 1, epsilon 2 2, which are the longitudinal strains, and epsilon 1 2, which is the same as epsilon 2 1 because you're talking about because epsilon is symmetric. So I can actually just write this as epsilon 1 2. It's just symmetric. So you have three unknowns here. As I said, that finding this is extremely difficult. So what you can do is you can measure epsilon 1 1 and epsilon 2 2. So we don't want to be, pasting the strain, it gets stuck to the surface. So you don't want to be pasting it once and then turning the angle in the x2 prime direction. So what the strain gauge is now giving us, it's telling us the longitudinal strains in the x1, x1 prime, and x2 double prime. Okay, so this strain gauge number 1 tells us the strain in 1 1 direction. Then the strain gauge number 2, it gives us the x1 prime direction longitudinal strain, and this third one tells us epsilon 1 1 double prime. So using these three, we can actually find out epsilon 2 2 and epsilon 1 2. I won't do that here. I mean, in fact, we have a problem here. So this is an example, a solved example. It's called, I don't remember let's take the example number here. This is 471. So they have a situation that's given to us in terms of a delta rosette, and you have to find the strain in two direction and 2 1 direction, or the shear strain. Okay. Again, how do we relate epsilon 1 1? It's quite straightforward. So let's think of so that's your x1 direction and this is your x2 direction, and then 1 1, so sorry, 1 prime direction was 30 degrees with the vertical. So this was 1 prime, so this becomes 2 prime. Now if theta is the angle here, so you can find the transformation matrix for this situation. Just remember, transformation matrix Aij was nothing but Ei prime dot Ej. you can easily find the transformation matrix. I won't give it to you. You can find it. Now theta for our particular case, in this case, is 60 degrees, right? But it could be any angle. So you can find the transformation matrix A for going from uh, x1, x2 to x1 prime, x2 prime. Okay, so when you do that, then you can relate your epsilon prime with epsilon, okay, because that basically tells you that epsilon prime is equal to A epsilon A transpose. So epsilons, you can write epsilon in terms of epsilon 1 1, epsilon 2 2, epsilon 1 2, and epsilon. These are the three unknowns, and you can write epsilon prime as well, and you can relate. So finally, what we get is, I can give you a relation when you simplify things. So epsilon 1 1 prime can be written in terms of the components of epsilon as so this is the relation that you have for epsilon 1 1 prime. Okay, so here epsilon 1 1 is known because that is being measured. Theta is known because theta for this case is 60 degrees. If you write for 1 1 double prime, the angle is 120 degrees. And these, this is known, and these two are not known. So epsilon 2 2 and gamma 1 2 are unknown. So you have two unknowns here, and you actually have two equations because one equation is for epsilon 1 1 prime, and you can similarly have one equation for epsilon 1 1 double prime, where your theta simply becomes 120 degrees. Okay. So you have two unknowns and two equations. So you can solve these equations, and you can get you can get the values of epsilon 2 2 and epsilon or gamma 1 2. Okay. So I'll just write here that epsilon 1 these three values are measured Okay, so you measure epsilon 1 1, epsilon 1 1 prime, epsilon 1 1 double prime, and you finally can calculate epsilon 2 2 and epsilon 1 2 using these. And you already have epsilon 1 1, so you get the complete information about the plane strain at that point P where you pasted the delta rosette. So the whole idea here is that measuring experimentally the shear strains is very difficult. So what you do is you use the idea of transformation. You measure the longitudinal strain in different directions, and you calculate epsilon 1 2 or the shear strain in that particular direction through the rules of transformation. Okay, that's the underlying idea of this discussion. So please try the problem. I have not put numbers here, but you can put the numbers as given in the problem, and you can calculate the values of epsilon 2 2 and epsilon 1 2.